There are different ways to reduce a quantity. Um, so we're gonna get into exponential reduction, although most of us call it exponential decay. That is the common name for that, exponential decay, not exponential reduction. But I want to compare those two ways of reducing a quantity down. Um, Many of us think of reducing a quantity by the same amount each time. Let's say you have a big box of tomatoes and you want to move them from one place to another place, without picking up the box. So you take, I don't know, 6 tomatoes. I guess it depends on the size of the tomatoes, and it depends on the size of your hands too. But you pick a few tomatoes, and then 5 or 6, and you put them wherever you need to move them, and then you go back to the box and pick up another 5 or 6 tomatoes and move them to the same spot, and you keep scooping away tomatoes. And so let's say you start out with 100 tomatoes, and let's say you pick um, 5 at a time, just to give an easy number. So -5, and then you keep doing that, -5. And so, of course, you got to do or make 20 trips, and eventually you get down to 0 tomatoes in the box. I know this is a silly example, but the idea is that we usually think of reducing the number of tomatoes in the box from 100 down to 0 by taking the same amount each time. So that is called arithmetic reduction, arithmetic downsizing. You scoop away the same amount each time. Many, many, many things in nature, in biology, in chemistry do not work this way. This is the way oftentimes we think of reduction, um, arithmetic reduction. Make a payment, for instance. When we buy a house, we make monthly payments, and we pay the same amount each month. Or when we buy a car and we make payments on the car, we make the same payments. So month after month. So we think of again of scooping up, taking things away, buy the same amount each time. When you buy a box of cereal, you usually eat a bowl a day or something like that. So it reduces by the same amount every day. Again, in nature, though, many, many things don't work that way. They work exponentially. So here, the first day, let's pretend you do this. Well, I know you're not gonna, well, I guess it doesn't matter. You're gonna move the tomatoes 1 a day, 5 a day, which wouldn't, it's not a good idea, because if it takes you 20 days to move the tomatoes, the last tomatoes are gonna be spoiled by the time you get to the last ones. But let's pretend they are something that doesn't spoil. Um, But in nature and in biology and in chemistry, things don't get reduced in this way. For example, if you take 100 milligrams of some kind of medication, um, the medication gets into your blood system, and then as soon as the organs, your body, and this is for everybody, as soon as the organs realize, oh, this is a foreign chemical. This chemical is not natural to us. This chemical shouldn't be here. As soon as the body detects that, then they start filtering that out. And so the kidneys and the digestive system and the lungs, perhaps, they try to get rid of all that chemical. That chemical should not be there. Even if it's a medication that is good for us, an antibiotic or something like that, um, the body doesn't know that. The body says, hey, this is foreign. This is not supposed to be here. This is not one of the normal chemicals we are supposed to have in the blood. So the kidneys and all other organs start moving that away, and so when the blood flows through those organs start picking up those impurities, let's call them impurities, even though they're medications, and you start, the kidneys taking them away. But the way it works is that they don't take away like 5 milligrams each time. No, no, no. They take away a big chunk of it, like 50 milligrams, half of it. over a period of time, let's say over 3 hours. And then um, the blood keeps circulating over our system, and it's still there's some milligrams of a foreign chemical that is still present. And as they filter that out, they take half of it out. So the next 3 hours, they take out 25. And then in the next 3 hours, the kidneys and the lungs and all the other organs that take care of this take away, 12.5. And then another 3 hours, and then they take away half of what is remaining, so 6.25. And then the next 3 hours, they take away, uh, half of that, and so very soon we are left with. By the way, what is left is the same amount in this case. So when we take away 50, then 50 is left over. When we take away 25 more, well, we take away 75 total up to this point, but then there's 25 left over. That's the beauty of doing the half measurement. Um, when we take half out, then there is going to be 12.5 left over, and so forth. So at this point, we have 6.25, let's say, milligrams of a medication in our body and I'm making the numbers up. So let's pretend these are 3-hour periods. So 3 hours, 3 hours, 3 hours, 3 hours. And then after 3 hours, there's going to be half of that. So that would be 3.125. And then there's a difference here. When we take the same amount each time, eventually we will run out of tomatoes or whatever we have to move, or if we're making payments to reduce a balance, as long as it has been calculated ahead of time that the payments will clear the balance eventually, then eventually you get down to zero. Purely mathematically, from a pure mathematical point of view, this progression, this decay, never gets to zero, because there's always a quantity left over, and then half of that and half of that and half of that is always a quantity. I mean, very soon we're going to get down to a less than 1 gram. So this is 15 because 30, 1.5, but then we got 12, so that's 6, and then we got a 2, 5. Okay, so in the next 3 hours, we're going to get less than 1 gram of this. So that is 15. So half of that is going to be 7, 16, 8, 25, 1, 2, 5. And then we can keep doing this. So the next time there's going to be like close to 0.40. This is close to 0.80. So then there's going to be close to 0.40, and then close to 0.10, rather 20, and then 10. But it looks like this never ends. Technically speaking, well, ideally, when you take any medication, listen to the whole thing I'm going to say. Technically speaking, when you take a medication, there's always going to be a particle in your blood. Ideally, there's going to be always half of the half of the half of the half, ideally. But that is not necessarily true. What happens is that the medication gets to be very, very small to the molecular level. You can only have one molecule left over. And eventually that molecule does run through the system. It gets picked up by one of the organs that gets rid of stuff in our system. And that one particle, one molecule goes away. So mathematically, it's like the asymptote. And actually that is what's going on. We start with a quantity, and then we have a decay, and then we have an asymptote. So from a mathematical point of view, this quantity gets to be, because we have an asymptote, gets closer and closer and closer to zero without ever being zero from a mathematical point of view. In reality, what happens is that this quantity gets to be as small as one molecule. So there's going to be one molecule, and that one molecule eventually gets filtered out. So yes, eventually we do get rid of all of the medication. It takes a while, actually not that long, because it fairly quickly we get down to a molecule level, and then you can get rid of it. And usually one molecule does not do much to our body, I think, anyway. I guess it depends on the chemical. The same thing happens when somebody drinks alcohol. You know, the body says, "Whoa, what's this alcohol in our system?" So the kidneys start working. I don't know what. To be honest, I'm not very um, fluent in biology. I don't know too much about it, but I do know that some organs. So I don't know exactly which organs are the ones. I'm guessing the kidneys, the lungs, um, other organs get rid of stuff, and eventually we get down to one molecule. That molecule gets to, again, the kidneys or the lungs, and gets out of the exits the body, and then we are free of that substance, whatever substance we have. At first, it goes down very, very quickly. It's about, well, we have to measure the time, and that can be done by experimentation because people have different levels of kidney performance and lung performance and other kinds of organs. But by experimentation, we can find um, how long it takes for a substance to go down half the way. And then once you know that, then the body is pretty consistent and will continue behaving in the same way. It will get rid of half of it in the same amount of time. So that time that it takes to get down to half whatever the substance we start with is called a half-life of a substance. So the time that it takes for a quantity to be reduced to half of it is called half-life. Okay. So in the experiment that I made up here, that this is just a made up problem. I'm saying the half-life is 3 hours. So every 3 hours, this goes down by a half. So the question is, well, how much is there going to be after 22 hours? Well, after 21 hours, you can do this 7 times, because 21 hours would be 1, 2, 3, 4, 5, 6, 7. Okay, so if we start with 100 milligrams of a substance and the half-life is 3 hours, there's going to be this much substance left after 21 hours. You can just make a table and do that. Well, there's other substances such as carbon 14. Okay, so let's do an example. Okay, so carbon 14. And again, forgive me, I do not know too much about biology. I believe this is present in many of the organic matter. And so as soon as the organic matter dies, then the presence of carbon 14 starts decaying. And I believe the half-life of carbon 14 has half-life of 5,700 years. Yeah, it takes a while. Now I remember what happens. I think there are 2 kinds of carbon, because the problem is with biology, if you try to figure out how long an animal has been dead, and by an animal we mean in the thousands of years. If you just measure carbon 14, that's not good enough, because we don't necessarily know how much carbon 14 there was when the animal was alive. And it could be an animal or a plant, such as a tree or something like that. So just one is not enough. We need 2 kinds of carbons. And then one decays slower than the other. And then by measuring the 2, then we can have a good approximation of how long the animal has been dead, or the tree, or whatever we are analyzing, organism uh, we analyze has been dead. But let's focus on one of them, because that the two carbons makes the problem more complicated. So let's just pretend we did know how much there was at the beginning, and now we just know, um, this measurement. So let's pretend you start with 100 units, okay, and after 5,700 years, how many units are we going to have? Well, it's the same thing as the problem here with what we have in our blood. After 3 hours, if we know that 3 hours is how long it takes for our body to get rid of half of the substance. By the way, let me make a parenthesis here. This is true under normal amounts of the substance. If you have a normal intake of medication or something like that, a foreign substance that you are taking, then this is the normal course of what's happening. There is such a thing as um, we can take too much of it, in which case our body might not be able to tolerate, might not be able to filter things out. So this assumes that we have a small amount, a reasonable amount that our body can get rid of normally. Yeah. So it takes 5,700 years, or 5,700 years, to go down to 50 units, or 50% of the initial carbon-14 we have. One question we can ask then is, well, how much carbon will there be after, let's say, 7,000 years? Yeah. So the question is, if we start with 100 units of carbon-14, how much is left over after, how much did I say? I forgot, but let's say 7,000 years. Question mark. Okay, so here we have a problem, because after 5,700 years, we're going to go down from 100 to 50 units. That is no problem. If we double this to 10,000, actually 11,400 years, 11,400 years, then this is going to go down to 25. So as long as we have a multiple of this, the half-life, we can go by halves and everything is cool. What if we go to 7,000 years? Things don't work the way we think they would. If we start thinking this way, try to figure out proportions, that's not going to work. Okay, so let's make that very clear. Because 7 doesn't go into 5,700 evenly, we cannot do the halves, and doing proportions will not work. Doing proportions will not work. So don't try proportions. Somebody could say, well, divide this by that, and then that gives you an idea of how much we got rid of, and then you get the proportional amount. Okay, let's do it so that we know what we're talking about. So if we did proportions, which is not supposed to work here, this is one way to go about it. Divide 7,000 by 5,700, and that gives you this much. So 1.22% of half-life. 7,000 is about 122% of half-life. If in half-life you get rid of 50 units, somebody could possibly reason, oh, okay, so if in 100% of the half-life, well, that sounds funny, we go down by 50, then in 122% of the half-life, we're going to get the same proportion. And somebody could think proportionally, okay, so that times 50 equals, so we're going to get rid of 61 units. And so let's subtract 100. We're going to end up with a negative number, but because I'm supposed to do 100 minus the number, but I'm aware of that. So we're going to end up with about 38.6. So that is about, if proportionally, we end up with 38.6 about units. But that answer should be wrong. That is the wrong answer. So this is wrong. Yeah, yeah. Because we don't take away the same amount. This thinking would be correct if we were making payments, if we were picking tomatoes from a box, the same amount, instead of two hands, using only one hand, proportionally, that would make sense. This thinking, that's why I wanted to differentiate between arithmetic versus geometric. This is also called geometric, exponential geometric. I take that back. I don't know if it's geometric. It is exponential. Yeah, I don't think it's geometric. It is exponential versus the arithmetic decay. So this is wrong. Let's just remember this. 38.6 is wrong. So how do we go about figuring out how much is left over? Well, there's a formula that we use which deals with exponential functions. So the current amount of a substance in anything that is decaying is equal to A sub 0. Sometimes we call it A naught. And then 2 to the negative, and then T over H, where H is the half-life of the substance we're working on. So again, H, with H being half-life of whatever substance we deal with. And this formula will work. For instance, in the current example we have, okay, 7,000 years. If we start out with 100 units, how much are we going to have after 7,000 years? Okay, so the amount equals 100 units we start with times 2 to the negative 7,000 over 5,700. So we're still going to end up with 1.22, but we're not going to use it with a proportion. We're going to use it as an exponent of negative 2. Okay, so we are going to use, well, I am going to use a graphing calculator. If you don't have a graphing calculator, you may want to use a phone, a computer, a tablet. Most of those devices will have an exponential key. And if not, you can probably access some kind of calculator on the internet. So let's do this. So we start with 100. 100 times 2 with the exponent, and I'm going to put the exponent in parentheses. So negative 7,000 over 5,700 and sorry, let me just check very closely. Yep, close the parenthesis, and we get um, about 42.7. So 42.7 about, so I'm not going to make it equal. That's rounding it, units, which makes a big difference with this doing it proportionally. So don't use proportions. In fact, I can see myself putting questions, multiple choice questions perhaps, where I'm going to give an answer that is proportional, correct proportionally. But of course, if we have exponential decay, then we cannot, that answer is going to be wrong. The correct answer is going to be an exponential answer, or corresponding to an exponential decay, which uses the exponent. Okay, and that is reasonable because after 5,700 years, we are supposed to get 50 units, and then 7,000 is not quite the 11,400 years. That is double the half-life. Remember, double the half-life doesn't mean that we go down to zero. Double half-life means that we go down to 25% of the original. Yeah, so here we have the original half-life, second half-life, that's 25%. Okay, let's do a second example. By the way, a lot of the substances they use as examples in the book have funny names, like carbon 14. They have a number attached to them, or radium. I don't know if they have a number or not, but so don't get confused with that number. That 14 in carbon 14, to the best of my knowledge, has nothing to do. This 14 that shows up in the name of the substance has nothing to do with figuring out the answer. It's just the name. That's part of the name of the substance. So don't get confused with that. Again, if you see a number with the as part of the name of the substance we are dealing with, it's just so that we can differentiate. I think there is a carbon 16, but again, don't quote me on that. I don't remember. So there are different kinds of carbons, and that's why they put a number to them to differentiate one from the other. And and if I'm wrong, please let me know, because uh, I don't know too much about chemistry actually. But let's think. So I have to make up problems such as the substance. So you're taking a medication, or you take, yeah, whether you take it via mouth or as a shot. There's a medication that goes into your system, some kind of, yeah, let's just call it a medication. Sounds better than drug. Um, Medication. And for easy numbers, let's start with 100 units. It could be grams or milligrams, and you know and we know that by experimentation that every 3 hours we end up with half of what we start with. So with 3 hour half-life. Okay, so if somebody asks how much is left over after 21 hours, so how much left over um, after, actually I'm going to use an easier number, after 9 hours, question mark. The answer is easy. You don't need, well, we are using exponential, but we don't need a, a fancy calculator to do this. After, so 9 hours is actually 3 periods of 3 hours. So we go down half, that's one, half, two, half, three. So that means that we are taking away 50, and then we're taking away 25. So that we're taking away 75 total. And then by the time we get here, we're taking away 75 plus 12. is 87.5. And if you take away 87.5 from adding those three from 100, then we get 12.5, which is a coincidence. It always gives us this number. So the answer is 12.5 units. Okay, so after 9 hours. How about after 8 hours? How about after 8 hours? You know, because usually when you take a medication, they spread it out. Well, I don't know if they still do that, but when I was younger, they would spread it out over, every 12 hours or every 8 hours, so that you would take 3 times a day the medication. So of course, by the time you take it again, the medication has gone down, but this number doesn't fit evenly into the half-life, so I cannot do that half and half and half anymore. So the question is, how much is left over? And we know there's going to be more than 12.5, because after 9 hours, this is how much is left over. After 8 hours, there's going to be more, because our body over time keeps taking the substance out, keeps cleaning our body. That's what our body does. It cleans itself internally from whatever substance we have. So after 8 hours, we should have more, but how much more? And don't use proportions. Proportions will give us the wrong answer. Maybe when the time is very close, maybe it will be a little okay, but let's just use correct exponential functions. So the amount is equal to the initial amount times 2 to the negative the time that we're looking at, 8, divided by the half-life rather. Boy, I'm thinking football halftime. 3, and that's it. And then we just punch that into our calculator. This calculator cannot quite do that kind of computation. And if it does, there's probably ways to go about it, but it would take too long. And I mean really long to approximate that with that other calculator. So let's see. So we got 100, and then we multiply by 2 with the exponent. I'm going to put the exponent in parentheses. So we got negative. Make sure, if you're using this kind of calculator, make sure you use this key, not the minus key. There's a difference between minus, which means subtract, versus the negative. And then 8 over 3, 8 divided by 3, close parenthesis. Yep. And then let me press enter. Let me double check this real quick. 15.75. So this is about 15.75 units. And you may be asking, well, how much should I round it to? In chemistry, that is very important. That has to do with significant units. And there is a process, and there is a very, very specific way of knowing how far we have to go. In mathematics, we pretty much tell you in the problem, round it to 2 decimals, round it to 1 decimal, which I understand by that as rounding it to the next decimal after the decimal point. So in this case, we're rounding it to 2 decimals, but that varies from problem to problem. If we have a multiple choice question, then hopefully the question itself will tell us how to round this correctly. So that's a different kind of question. You know, that's part of the question. I'm not concerned with how we're going to round the answer here. That's a different matter. It is an important matter, but it is not something that we want to address right now. We want to address how to get this number, and that is the formula. So things that decay are chemicals in nature. substances that are in our body, they decay um, exponentially. And perhaps other things that I cannot think about right now, but a lot of things in nature, in biology, in chemistry, do decay. If they decay exponentially, there's also um, growth. There's exponential growth. So if you put organisms and they have plenty of food and space, they will reproduce at an exponential rate. If there's nothing that causes them to stop living and reproducing, such as a limitation in space or food or predators or diseases, then they will just grow exponentially if that is the case. Um, yeah, but I wanted to focus more on the decay. That's what I wanted to do in this video. Um, there is the other question of how long it will take for a substance to go down from 100 to 20, which implies we have to solve for the exponent. That is going to be a question for a different video, because we have to introduce the inverse of exponential functions, which where the exponential functions were part of the previous video. This video deals with one of the applications out of many, many applications, just the decay. There's also growth, but I'm not touching growth in this video. And but we cannot solve for the exponent until the next video, which is going to be about, or maybe even two more videos after we see logarithms. So I think we're going to stop here. Again, the one thing I want to emphasize and drive is please distinguish between arithmetical decay, where you take away the same amount, versus geometric. No, I'm sorry, I misspoke again. Not geometric, exponential decay, where we take a chunk, a proportion, a percentage, and then we take the same percentage over the same amount of time out, and then the same percentage of what is left over after the same amount of time, and so forth. So things reduce more quickly than in this way. It looks like this is fast, but actually this is faster. All other things being equal. All right, we will stop the video here.